So our number one tool that we want to use when we're doing homework or quizzes or tests or the deep dive discussions or even projects is probably going to be your formula card if you're doing the projects by hand at least. So the formula card has all of the formulas we need, and then in the third column, I'm not sure showing the third column right now, it has the calculator shortcuts that we need. So whether you're doing the problem by hand or with a calculator, the formula card has it all. I'm not showing the calculator shortcuts here because the margin of error formulas don't have calculator functions that we can use. So I'm just showing the formulas. The margin of error for means formula is the one that we want because it says find the margin of error for estimating the population mean. So that's margin of error for mean formula. It has a t-score, but we won't end up using the t-score, and I'll show you why in just a second when we look at the t-table. And then it's times s. S is the sample standard deviation, and then it's divided by the square root of n being our sample size. So the t-score, and it has this subscript alpha, but we can kind of ignore that. That's just saying that it depends on the confidence level that the t-score changes depending on the confidence level. It also changes depending on our degrees of freedom. So here the subscripts all refer to this right tail probability, but we said for a 95% confidence interval, it turns out that alpha is the right tail probability, but if you're doing a 95% confidence interval, you end up splitting the 95% is in the middle, and then you have 2.5% on each tail. So the right tail will have 2.5% or 0.025 area, and that's what that 0.025 means. But you don't really need to know that for this chapter, and you only need to know it for a very special type of problem in the next chapter. This problem tells us 95% confidence interval, and so we know that this middle column's the one we want because it's the 95% column. And then degrees of freedom is n minus 1. We have a sample size of 484, so we want degrees of freedom of 483, but our table only goes to 100. And whenever we got anything significantly more than 100, rather than the 100 row, we'll use this degrees of freedom of infinity row. And the degrees of freedom of infinity row is actually the z-score, because remember in the video for chapter 8 when we talked about the t-curve, it gets closer and closer and closer to the z-curve the more data that we have. And so we're just essentially going to do the z-score. Remember, we're in the middle column for 95%, so going down to degrees of freedom of infinity, and we get the very familiar, or what should be very familiar to you now, z-score of 1.960. So that's our z-score, and we'll actually use it for both of these because our degrees of freedom will be even more here, 1520, once we subtract the 1. So we'll be using 1.960 for both of them here. So going back to our formula, we want our t-score, which we'll use as our z-score, of 1.960. And then we'll want to multiply times s and divide by the square root of n. Let's see, our s was 110, so times 110, and then divided by, and we're still using this formula, well, actually this formula right here, s divided by the square root of n, so square root of n, which is our 484, and I bet that happens to be a perfect square, but and then we get 9.8 exactly. So if it says 2 decimal places, you might want to say 9.80, but it's pretty exact. I guess you could get a more precise t-score than that, and this says 9.82, but I'm sure it accept 9.80, yeah, plus or minus 1%, so it would accept 9.80 as well. I'm not sure where they got the 9.82 from, because it should be, I mean, you can't get much more, we'd use 4 digits of accuracy here, and this is exact, so I'm not really sure how they got off by, maybe they used less precision on their t-score, but have to be just 2 digits. Yeah. And then for the second one, we've still got everything the same except N. I'm just going to second entry and change this to 1521 because that's the only thing that should change. We're still using the z-score for 95%. We're still using 110. We've just changed the sample size, and so now we get 5.53, which is exactly what they got. So, and then you can answer the last question. Our sample size increased, and we see that the margin of error decreased. So as the sample size, the larger the sample size, decreases our margin of error, and that's because the sample size is in the denominator. It's square rooted, but even the square root of a larger number is still a larger number. But putting a larger number in the denominator, like 1/2 versus 1/10, or 1/2 versus 1/1000th, the larger number in the denominator makes the whole number, or the fraction number, I guess you would say, the fraction itself makes it smaller. And so that's how we would do this one.